Alrighty, so section 1.2, we're getting into the beginning part of just talking about unit circles. Now, basically, when you're talking about unit circle, the idea is it's a circle centered at 0, 0 with radius 1, right? That's why we call it a unit circle. So we're going to actually use this idea of unit circle to help us come up with our trigonometric functions, use them to define them, and then, of course, try and use it to solve some of these examples. So again, keep in mind, when we're talking about a unit circle centered at 0, 0 with a radius of 1, so if we're talking about putting this on our coordinate plane, then of course, if you think about splitting this up into 4 equal parts, we would be starting at our 1, 0. Remember, that's our standard position. So starting with 1, 0, we're of course going to 90 degrees, which would put us at the ordered pair 0, 1. At 180 degrees, we would be at negative 1, 0. What would this be? 270 degrees would be at 0, negative 1. And of course, when you complete your circle at 360, you're back to that first point you started out with, which is at 1, 0. Now, the idea here is we are talking about, taking our real number line and just wrapping it around our unit circle. So the idea is you would place the point 0 of the number line here at this point 1, 0. We're taking the positive side and wrapping it, of course, in the counterclockwise. Remember, we talked about this last time, that counterclockwise our angles are positive, clockwise angles are negative. So that's kind of what we're using with this number line idea also. So we're taking the positive side and wrapping it counterclockwise. We're taking the negative side of our number line and wrapping it clockwise, okay? So the idea here is if you take a number that corresponds to our real number, and they're just calling it t, so think about it as number 4, or you can think about it as any of those positive numbers. As we take that number line and put it on our circle, the idea is this real number value will be corresponding to a point on our line, right? So it's going to be of the ordered pair x and y. Again, we're familiar with putting our values in alphabetical order. So x value goes first, y value goes second. So the idea is, like I said, take your number 0 from the number line. It will correspond to the point 1, 0. Now we know we're making an entire circle, which means when we come back to that same point 1, 0, we're going to be at an angle of 2 pi, right, or 360 degrees. Now 2 pi is approximately what, 6.28 if you take the double of 3.14, which means that point 6.28 with its decimal approximations will basically come back and fall on our same point 1, 0. So that's kind of what they're talking about if you think about the circumference of that unit circle. So you can use that idea to, of course, build it up with our arc length calculation here. So again, they're saying that real number t corresponds to our central angle of pi, if you're keeping it in the standard position, whose radian measurement is also going to be t. So the idea here is if you look at s equals r times theta, your formula for arc length, radius being 1, we know the arc length is going to be the same value as our theta. And we had kind of talked about this a little bit also in section 1.1. So basically that real number t, again from our number line, is also going to be the length of the arc that is being intersected by this angle theta. And again, we're in general thinking of our angles in radians for most part. Now, before I actually get into this discussion with trigonometric functions, I actually do want to talk about the unit circle just a little bit more. So let's get into our, okay, let me see. Actually, let me draw a circle. There we go. Okay. So So if we think about this as our unit circle, we've got our 1, 0, 0, 1, negative 1, 0, 0, negative 1, right? Just following our points. Okay, so now think about this. If we are talking about dividing our circle into 4 equal parts, that basically means on the upper half we're dividing in 2 equal parts, right? So if you just think about this distance here in terms of angle measurements, we know we're starting at 0 radians or 0 degrees. We know this is going to be pi over 2. This is going to be pi, and this one here is 3 pi halves, right? Now think about it in this way, because you know that's something we will be working with depending on how many equal parts we break our circle into. And we had kind of again talked about this a little bit in section 1.1. So here, the idea is if I am taking the distance between pi and 0, this little part, I'm dividing this into 2 equal parts, because I'm dividing my circle into 4 equal parts, right? So half a circle in 2 equal parts, I end up getting pi over 2. That's basically where this value is coming from, just dividing it into 2 equal parts. Now, if I think about breaking this down into 4 equal pieces for the first initial starting point, you can think of that as being 0 multiplied into pi over 2, which will of course always be 0. 1 multiplied into pi over 2. That gives me my second marker, or my end of the first piece. I'm breaking this up into 4 equal parts. So that's 2 pi over 2, which is where that pi comes from, right? Now we're breaking this up into the third piece. 3 pi over 2, which is where this guy comes from. And then my fourth marker, or the end of my complete circle, which is my 2 pi, that's going to be right here, right? Now, if I use that same idea, same calculation, but instead of breaking my circle into 4 equal parts, let's say we want to double that and break it up into 8 equal parts. So how can we basically translate this into breaking it up into 8 equal parts? And let me get us another circle here.
So you could start out by breaking it out into the 4 parts that you did before, and kind of those in halves. That would be 1 or pi over 4, and then pi half, and then 3 pi over 4, and then pi, and then you just keep adding pi half to each.
Not very straight, but it's okay. Alrighty, so we're breaking it up into the half a circle into 4 equal parts then, right? Mm-hmm. So obviously we are still going from 0 to pi, right? Because those angles will stay the same, but now instead of dividing it up into 2 equal parts, we're dividing this up into 4 equal parts. So what will all of those calculations come out to be?
So it's just the same thing as before. So 0 pi or pi
So
half.
that will actually be this angle here, and then so pi over 4.
And then 2, 2 pi or pi over 2. And then 3.
So that's obviously back at that 90-degree measurement.
And then 3 pi over 4. And then you're back at pi.
4, right, because that's going to be 4 times pi over 4.
And then it's going to be 5 pi over 4.
Very good.
And then you're back at 3 pi over 2.
Because that will be 6 times pi over 4, so that will be back at that 270 degrees. Okay.
And then 7 pi over 4.
Very good.
And then you're back at 2 pi after that.
Very good. Yeah. So basically the idea is, and I'm not going to get into all the different breakdowns, but we should be able to do this with 4 equal parts, 8 equal parts. It's okay, ignore him. So with 12 equal parts, what would our denominator look like? Oh, think about this. This was 4 equal parts. So for most part, what was our denominator? 4, right? Unless in the places where it simplified. Most of these were with a denominator of 4. So what happens with 12 parts is most of your denominators will actually be 6, right? Because you're going to be breaking half your circle into 6 equal parts, which would follow the same idea. I think they also do this for 6 equal parts, so you will see a denominator of 3. So if we actually go and look at our unit circle, which was a copy I gave you guys last time. So if you look at those radian values inside of your unit circle, you will notice that when we are doing this in 4 equal parts, that's your 0, pi halves, pi, and 3 pi halves. Your 8 equal parts are again 0, pi over 4, pi halves, 3 pi over 4, pi, 5 pi over 4, 3 pi halves, 7 pi over 4. So all those denominators of 4 are telling us we're basically breaking the circle up into 8 equal parts. Denominator of 6 is the 12 equal parts. Denominator 3, of course, is 6 equal parts. Now, each of these angle or theta values are corresponding to a point on our circle, right? And you will see those are written as ordered pairs in our x and y ordered pair system. So again, you should notice those 4 main points that we talked about are 1, 0, 0, 1, negative 1, 0, 0, negative 1, and then of course we're getting into smaller values as we go into these equal amount of parts. So let's get back. Yeah, this guy here. So the idea here is when we are actually talking about our ordered pairs corresponding to that real number t from our real number line, then those ordered pairs x and y can actually be used to define our 6 main trigonometric functions. So you can see those trigonometric functions are sine, cosecant, cosine, secant, tangent, and cotangent. Of course, your 3 main functions are your sine, cosine, and tangent, and their reciprocals are the cosecant, secant, and cotangent, and you can see the abbreviations for all of those functions right here underneath where we're defining these. So as you can see, we're actually defining the sign for this real number t as y. So that's actually going to be this y from our ordered pair here. Your cosine of t is defined as the value x. So a lot of times you will actually see these ordered pairs being written as cosine for x and sine for y. And again, remember about the idea of ordered pairs. So think about c. For cosine will come before s for sine, right? If you again follow the alphabetical order. So we always put cosine for x and sine for y, and then it's just a ratio of those values for defining the other function. So I actually want to talk about a little bit about how we come up with these definitions. And for that, I want you to go to your first supplement handout, which was this one here. And we'll actually be coming back and revisiting this, but I actually like this definition better of how we come up with our ratios for sine and cosine, tangent, and all the other functions. And you guys may remember this. We had talked about this in college algebra also when we had introduced the distance formula and the midpoint formulas. where we talk about how we can actually use the Pythagorean theorem to help us come up with the equation of a circle. So we're actually kind of rounding back to that. So if you think about on our coordinate plane, putting our little right triangle in the standard positions, of course your initial side is right here on the positive x-axis. The terminal side for our angle theta is in that first quadrant. So this distance x, this is distance y, and then the hypotenuse is our distance r, the radius of the circle that is formed. So using that Pythagorean theorem, we're coming up with x squared plus y squared equals r squared. Now remember, again, as I said earlier, your r happens to be 1 when you're talking about a unit circle. But of course, the beauty of the right angled trigonometry is it doesn't mean it only works for a unit circle, right? That will work for any right triangle. So we're just using this idea of right triangles to help us come up with the definition for our 6 trigonometric functions here. So again, you've got your sine, cosine, and tangent, and their reciprocal functions are cotangent, secant, and cosecant. So the way we define this, if this is our angle theta right here, and it can be any measurement, it doesn't matter. The side opposite from that angle is what we call as the opposite side. The side that helps you form the angle is what we call as the adjacent side. And the side across from your 90-degree angle is always going to be the hypotenuse, which for us will represent the radius of our circle, okay? So your relationship is defined as, with respect to the theta, for sine function, it's going to be opposite over hypotenuse. For cosine, it's going to be adjacent over hypotenuse. Tangent actually ends up being a ratio of your sine and cosine function, right? So you have opposite over adjacent. And then look at this. For sine function, its reciprocal is the cosecant. So if sine is opposite over hypotenuse, the cosecant becomes hypotenuse over opposite. Cosine adjacent over hypotenuse, its reciprocal is the secant function. So that will become hypotenuse over adjacent. For tangent, its reciprocal is cotangent. So opposite over adjacent will become adjacent over opposite. Now you were saying about how to help you remember, right? Now different textbooks actually give you different little things to remember these functions by, but I actually learned it by using these 3 little words, okay? So to remember the order of the sine function, think about so, that's S-O-H. So that's sine, O for opposite, H for hypotenuse. So that's sine, opposite over hypotenuse, right? The ka, C-A-H, is cosine, adjacent over hypotenuse. So that's our cosine over here. And TOA is, of course, tangent with opposite over adjacent. Yeah.
Will we be doing much with the trig identities, like if tangent equals cosine by, I don't know.
Oh, yeah.
Yeah.
Sorry. Yeah, because this is all going to be about bringing those identities in, equation solving, and all of that kind of thing.
So what about cosecant and cosecant? Since you don't have one for that.
So yeah, so here's the other thing. So the main 3 functions are your SOHCAHTOA, okay? For the reciprocal functions of that, here's how I remember it. So for the sine function, its inverse actually starts with a C. For the cosine functions, its inverse starts with an S. So you're not going to have sine with secant, right? Because they both start with an S. So sine has to go with cosecant. Cosine has to go with secant. Tangent is probably the easiest one because it says tangent and cotangent. So they are reciprocals of each other. But the idea is to remember that S goes with C and C goes with S for your reciprocal functions. And so if you know that for sine, the reciprocal is cosecant, then you're changing the order of O and H, right? It's going to become HO. So that's your hypotenuse over opposite. For the cosine function, its reciprocal is secant. So AH will become HA, so hypotenuse over adjacent. And for TOA, cotangent, which is the reciprocal of tangent, is going to become AO, so adjacent over.
So you just flip it basically?
So if you, yeah, you're just literally inverting your fraction. So if you can remember the main 3 functions, SOHCAHTOA, then basically inverting that ratio is going to give you your reciprocal functions, and then remember S goes with C and C goes with S. And as I mentioned, tangent goes with tangent. So basically tangent and cotangent are reciprocal functions of each other. I have actually put a couple examples here for just for you to practice a little bit. So remember, we use capital letters for the angles and small letters for the sides of the triangle here. So when they're asking you to find sine A, they're basically asking you to figure out what this ratio for our sine function is going to be. So just using this, let's do a quick couple examples here to help us out. Okay, so this is TOA for the reciprocal functions. S goes with C, C goes with S. So that means for sine, its reciprocal is going to be cosecant. For cosine, its reciprocal function is going to be secant. And for tangent, it's going to be cotangent. All right, so that first example, we've got A, B, C for the angles, small letters A, B, C for the sides. And normally, you can think of your theta being here, but in these examples, we're actually changing the location of theta just so that we are comfortable with these ratios. So your angle can be any one of these, and then of course this is our 90-degree angle. So for the first example, they're asking us to find sine of angle A. So if this is our angle A right here, we're talking about sine, so that's right, OH, that means opposite on the numerator, and the hypotenuse on the denominator. So with respect to angle A, which is right here, the opposite side is this side A, and the hypotenuse, of course, is side C, and then just use the numbers that they're telling us for A, B, and C to come up with that ratio. So they're telling us A is 5 and C is 13, right? So just using those numbers. Looking at 5/13. Of course, when we get into other examples, we'll probably do fractions, we'll probably do decimals, just depending on what they're asking. Right now, we're just trying to get comfortable with our ratios for this definition here. The next one is asking you to find cosine, but this time of angle B. So remember, for cosine, it's ca, C-A-H, which means you have the adjacent side over the hypotenuse side when you're defining cosine. But now you're doing this with respect to angle B. So with respect to angle B, which is our adjacent side, A, hypotenuse, of course, will stay the same at side C, right?
So the one that changes adjacent and
Depending on which angle you're using, exactly. So you'll notice this actually comes out to be the same value, right? 5/13, but you're still using the same length, you're just changing the angle that you used. So this is not on your handout, but now tell me, if I wanted to find out what is cosine of angle A for this specific triangle, what would be?
It would be B over C, so it would be 12/13.
Yeah, very good, because if we go back to angle A and talk about cosine for angle A, that's again going to be adjacent over hypotenuse. In this case, that would be B over C, which is 12/13. Okay, very good. Alrighty, let's do number 4 so we can talk about the tangent function here. So this time they're telling us the values of A, B, and C are 9, 12, and 15 respectively. So here you will of course see that some of these values can be reduced down, right? So anytime you're working with fractions, we always want to reduce our fraction. So let's look at 4, tangent of A. So remember now, tangent is TOA, T-O-A, which means the opposite side goes on the top, adjacent goes on the bottom, right? We're still keeping the same values here. So when we're talking about opposite over adjacent, that's going to be A over B. But now for this triangle, they're telling us A is 9 and B is 12. So what does that reduce down to? There you go, 3 over 4. Always remember to reduce your fractions. Okay, so using that same idea, let me see what values you guys can come up with for that last triangle. 5, 6, and 7. Okay, Sydney, what do you have for the first one? Sine A.
8 over 17.
All right, let's see. So you are doing sine of A, which will be A over C. 16 over 34, and you basically reduced by 2, yeah, right? And especially since 17 is a prime number, we can't really break it down any further than that. Did everybody get 8 over 17? Yeah? All right. Adrian Medina, can you tell me about 6, tangent of A?
So it's 16 over 30, and then you reduce it to 8
Right, because
over
you're
15.
looking at opposite over adjacent, right? So that would be A over B. So 16 over 30, and what did that reduce to?
8 over 15.
8 over 15. Because there's nothing common further than that, right? Alrighty. Ezra, can you tell me 7?
7, I got 8 over 17, so it's gonna be adjacent over hypotenuse, so it's 16 over 34, and we just reduce
Okay, what angle are they using here though?
angle B.
Okay, so angle B, you're looking at
Is
adjacent, which would be still your side A,
Mhm.
right? And of course, cosine is always over the hypotenuse, so you're still using A over C, which actually is the same as sine of angle A, right? Because you end up with 8 over 17. So you should actually notice that our sine of A is coming out to be the same ratio as cosine of B, right? We saw that happen here in those first triangle. We're seeing the same thing happen here. Okay, what I would like you guys to do is for all 3 of the different measurements, do the 3 reciprocal values. So cosecant, secant, and tangent, okay? And we'll look at that next time. So work on those for each triangle, each different measurement, do the reciprocal trigonometric functions. Alrighty guys, so we'll stop here and then we'll pick up with 1.2 when we come back on Thursday.